Welcome to the Bentley Systems training course where you will learn how to generate seismic loads in STAAD.Pro Connect Edition according to the modal response spectrum procedure as outlined by the ASCE 7, section 12.9. Now before we begin investigating or generating loads in our sample model, let's take a look at some of the code requirements that are outlined in the ASCE 7. The ASCE 7 allows 3 different methods for generating your lateral loads, including the equivalent lateral force procedure, the modal response spectrum analysis, and the response history or time history procedure. Before beginning, you should review Table 12.6-1 in the ASCE 7 to determine which analytical procedure is appropriate for your particular sample structure. Now for our training today, we are going to assume that the equivalent lateral force procedure is not permitted, so we'll be using a modal response spectrum analysis. Since we have determined that we will be generating our seismic loads according to the modal response spectrum analysis, we should be getting familiar with section 12.9 of the ASCE 7. Over the course of this training, we are going to show you how to incorporate all of the different code sections into your STAAD.Pro model to ensure that all of your dynamic seismic loads have been generated considering the requirements of the code. Over the next series of videos, we are going to complete our workflow for generating the modal response spectrum procedure, which will include the process of modeling your dynamic masses, defining your modal response spectrum load items, specifying your maximum number of mode shapes, and then finally performing the analysis and reviewing the results. At each step where we're going to be referring to a particular code section, we will outline that information for you as well. We will now turn our attention to our sample model in STAAD.Pro Connect Edition, and we are going to be starting by considering our problem statement. Over the next series of videos, our goal is to generate seismic loads in STAAD.Pro Connect Edition using the modal response spectrum procedure as described in the IBC and ASCE 7 design codes. Before you begin, you should take a few moments to review your sample model and the seismic design requirements that are now indicated on your screen. In addition to considering your seismic design requirements, you should also get acquainted with this model, as we're going to be beginning with a model that's already been created in STAAD.Pro. As you can see, all of your geometries, properties, and materials have already been assigned to the model, including all of your support conditions. If we took a look at the specifications area, we're also going to notice that a rigid diaphragm has been defined for each level of this particular structure using the floor diaphragm command. Now in the ASCE 7, section 12.9.5, the distribution of horizontal shear shall be in accordance with the requirements of section 12.8.4, except that amplification of torsion per section 12.8.4.3 is not required where the accidental torsional effects are included in the dynamic analysis model. Now, if we were to refer to section 12.8.4, the horizontal distribution of forces shall include torsion when the diaphragms are not flexible, which will include inherent torsion and accidental torsion. Now, since a rigid diaphragm is present at each level of our structure, the static and dynamic seismic loads must consider torsion. Let's also take a look at the loading area of the program. And I'm going to go ahead and expand my definitions area and also my load case details section. Now what you're going to notice is that we've already generated seismic loads according to the IBC equivalent lateral force procedure in the X and Z horizontal directions. Now even though we will be designing the structure using dynamic seismic loads according to the modal response spectrum procedure, we have still generated static seismic loads according to the equivalent lateral force procedure. The static seismic loads will be used to ensure that the code requirements of the ASCE 7, section 12.9 are incorporated into your design. What we're also going to notice for these static seismic loads is that we have included accidental torsional moment and also natural torsional moment in the design as is required by the design standard. We will now begin our workflow for generating our dynamic seismic loads by modeling our dynamic masses for the structure. For this workflow, we're going to be using reference load definition to create our seismic masses. So let's start by creating a new reference load case. In the load and definition dialog, I'm going to highlight the reference load definition, and I'm going to tell the program that I want to create a new reference load case by clicking on the appropriate icon in the Loading tab of the ribbon toolbar. I'm going to title my reference load case as Dynamic Mass, and I'm going to select the loading type of mass. In the loading type, I'm going to make sure that I select the mass item. Now, this reference load case will be used for two primary purposes. The first purpose is it's going to be used to define my dynamic masses for my loading. And it's also going to be used to calculate the center of mass and the mass associated with each rigid diaphragm. Once we're done, we'll go ahead and click the Add button, and then we'll click Close. And we can see our new dynamic mass load case is now available. Let's go ahead and populate some load items within this load case. So I'm going to highlight my dynamic mass load case, and then I'm going to come up to my loading tab in my ribbon toolbar and tell the program I want to create some new load items. Now within this dynamic mass load case, I need to specify the masses in terms of weights and in the directions which they are dynamically active. You would also traditionally define all of your masses in their absolute value format to ensure that all of your masses are able to be effectively added together instead of canceling each other out. Now, according to the ASCE 7, section 12.7.2, the effective seismic weight shall include the total dead load and other loads, including some storage loads, partition loads, equipment loads, and flat roof snow loads. So you want to make sure you refer to that section of the code to ensure that all of your dynamic masses are defined appropriately. For our particular structure, we're going to use the self-weight and the floor load options to define all of our masses. Let's go ahead and start with the self-weight load. And I'm going to define this with a positive value in the X, Y, and Z global axis directions, since I'm assuming that my structure can vibrate in all three directions. So I'm going to select my X direction, +1, click the Add button. I'm going to define this load in the Y direction and also finally the Z direction. Let's go ahead and now select our floor load option. Now within the floor load area, we're going to define some load, our dead load, on each level of the structure. And we're going to assume, in addition to the self-weight of the structure, that we have a superimposed load on each level of 0.02 kips per square foot. This is going to be applied again in the X, Y, and Z global axis directions. And what I want to do is I want to select a range that's below my first level of structure all the way up to above my roof. So I'm going to go from 5 feet to 45 feet for this exercise. We'll go ahead and click the Add button. We'll define this load in the Y direction and also the Z direction. Now all of the loads that I specified so far are considering the self-weight of my structure and the superimposed dead load. But I'm also going to assume that the first floor of my structure contains some storage loads. So according to the code, 25% of that storage load also needs to be considered for the dynamic masses. So I'm going to define that load as 0.06 kips per square foot. And I'm going to apply this load just to the basement level, as that's the only level that has that type of load on it. I'll go ahead and define this in the global X direction, again, the global Y direction, and the global Z direction. Now you can use any of these load items over in the left-hand pane to define your masses as they are present on your particular structure. I'm going to assume for my structure that the self-weight and the floor load items are what is needed. So I'll go ahead and close out of that. Now, as I take a look at this dynamic masses reference load case, I'm going to see that all of my floor loads are automatically assigned. If I were to click on them, I could see the colored hatching area, which basically indicates the tributary load that's going to be assigned to each member, as floor loads are automatically converted to a member load. But I'm also going to see that my self-weight needs to be manually assigned to the structure. So I'll go ahead and assign these to every member in the model. Now the self-weight and all of the loads within this load case are just used to calculate the masses on the structure. We're not adding any additional dead load or live load to our structure, as the load type on this load case is specifically entered for mass. Now that we have defined all of our dynamic masses for the structure, we are now ready to move on to the second step in our workflow, which is to define the modal response spectrum load items. If I were to look at my sample model in the load and definition dialog, expand your load case details section, and you're going to notice that we've already created 4 dynamic seismic load cases to represent the direction that we're going to be considering our dynamic seismic loads in, including the positive and negative effects of eccentricity. When you're ready to define your new modal response spectrum load item, you're going to highlight the first load case for dynamic seismic load. And then we're going to go up to the ribbon toolbar and click on the Load Items icon within the Loading tab. Once in the Create New Load Items dialog, we're going to find our Response Spectra item. Now we're going to take a look at the different parameters that we can define. Now in STAAD.Pro, we are allowed to enter our custom parameters, or we can enter some code standards. For this model, we're going to select the IBC 2015 or the ASCE 710 code. As you can see, most of the parameters have now become active as we've selected a design standard. Next, we're going to take a look at the combination method. Now, according to the ASCE 7, section 12.9.3, the value for each parameter of interest calculated for the various modes shall be combined using either the square root of the sum of the squares method or the complete quadratic combination method. Now, the complete quadratic combination method shall be used for each of the modal values or where closely spaced modes that have significant cross correlation of translation and torsional response. For this model, we're going to select the CQC method, which is the complete quadratic combination. Next, we're going to enter all of our code parameters, including the long period transition, our FA and our FV parameters, along with our site class. Following that, we're going to enter our zip code of our structure, which will automatically populate the SS and the S1 parameters. We're going to select a spectrum type of acceleration, an interpolation of linear, and we're going to enter a 5% damping. Next, we're going to specify our direction, and this load case represents seismic load in the positive X direction. Now, according to the ASCE 7, section 12.9.2, the value for each force-related design parameter of interest, including story drifts, support forces, and individual member forces for each mode of response shall be computed using the properties of each mode in either section 11.4.5 or 21.2 divided by the quantity of R over I. Now, to incorporate this requirement into the calculation of our seismic loads, we are going to set the factor equal to 0.156, which was calculated using a response modification factor of 8.0 and an importance factor of 1.25. Now, by nature, a modal response spectrum analysis will be an iterative process. We're going to use this as the starting point for our scale factor, and we may need to come back later on after the analysis is performed and adjust this parameter to ensure that our results are in accordance with our code requirements. Next, we're going to take a look at our torsional area. So we're going to set our Use Torsion checkbox to be an on. We're going to enter our dynamic eccentricity as 1.0 and our accidental eccentricity is 0.05. Now, according to the ASCE 7, section 12.9.5, the distribution of horizontal shear shall be in accordance with the requirements of section 12.8.4, except that amplification of torsion per section 12.8.4.3 is not required where accidental torsional effects are included in the dynamic analysis model. Now, to incorporate this requirement into the calculation of the seismic loads, we will include the dynamic eccentricity, which includes inherent torsion in the rigid diaphragm, and the accidental eccentricity or accidental torsion. As another note, all of the design parameters, including our SS and S1 factors, along with our FA and FV factors, are the same factors that were used for the equivalent lateral force procedure static seismic load cases that were already created in this model. It's important that all of the parameters are consistent throughout the design so that when you are checking your base shear of your structure for your static and your dynamic load cases, they are appropriately compared together. Now, once we're done, we'll go ahead and click the Add button, and then we'll click the Close button. And we can see that now our first modal response spectrum load item is created. Now, we're going to repeat this process for the additional load items or the additional dynamic seismic load cases. Now, you're also going to notice that each of these load cases does correspond to a static seismic load case that was already previously created. So we'll go ahead and complete this process for the remaining 3 dynamic load cases. Now, all of our load item parameters are the same between the two, except the direction may be different and the positive or negative effects of eccentricity may be different as well. Now, this completes the process of adding in your modal response spectrum load items into your STAAD.Pro model. After the dynamic masses are modeled and the dynamic seismic load cases are added, you are ready to move on to the analysis phase of your workflow. To start this process, we're going to go to the Analysis tab in the Workflow page control area. Now, the first command we're going to invoke is the Cutoff Mode Shape command. You can find this command in the Analysis and Design tab of the ribbon toolbar under the Miscellaneous Commands icon pull-down menu. Now, this command is used to instruct the program to extract a specific number of modes during the modal calculation, during a response spectrum analysis and a time history analysis. We're going to specify the maximum number of mode shapes for this exercise to be 6. Now, the ASCE 7, section 12.9.1 states that the analysis should include a sufficient number of modes to obtain a combined modal mass participation of at least 90% of the actual mass in each of the orthogonal horizontal directions of response considered by the model. Now, to incorporate this requirement, we will instruct the program to include the first 6 modes into the calculation. After the analysis is complete, we can review the mass participation and adjust the maximum number of mode shapes as needed to achieve at least 90% mass participation. To invoke this command, we're going to finish this process off by clicking on the OK button. In addition to that, we're also going to define our analysis commands. Now, it is a program requirement that all dynamic seismic load cases can only be included in a linear elastic analysis. To invoke that command, we're going to go to our analysis dialog and click on our Define Commands button. We're going to perform a linear elastic analysis, and for our print options, we're going to instruct the program to print our mode shapes. This will give the output file the additional information we will need in order to verify our analysis results. We'll click the Add button and then finish this off by clicking Close. Once our model is ready for the analysis, we're going to save and then run the analysis, which is available on the Analysis and Design tab in the ribbon toolbar. After the analysis is performed, we're going to verify that we don't have any errors or warnings that were reported. If we're satisfied, then we're going to move on to the next phase of reviewing our results. So we'll click on the View Output File radio button and then click Done. Now, the first thing we're going to check upon entering the output file is our mass participation. If we look over in the pane over at the left-hand side, we will find some participation factors items. There's going to be a quick link for each of the dynamic seismic load cases that we included in this model. So we should have 4 different links for that. In the output file, we're going to take a look at each of our mass participation factor tables and verify if the sum x and the sum z values for the last mode shape that was calculated is greater than or equal to 90%. Now, according to our results, mass participation in the x and z directions is greater than 90%, so 6 modes was sufficient for this particular structure. Now, if you don't achieve at least 90% mass participation in the orthogonal horizontal directions, you will be needing to return to the modeling mode, increase your number of mode shapes using the cutoff mode shape command, and then reanalyzing the structure before going any further. As mentioned earlier, a dynamic seismic analysis will be an iterative process. So we can review the mass participation factors for each of the dynamic seismic load cases, and we are going to notice that for all of them we did achieve at least 90% mass participation. Let's go ahead and get back to the top of our output file. The next thing we're going to take a look at is we're going to take a look at the base shear of our structure, and we're going to be comparing the base shear of our static seismic load cases with that of our dynamic seismic load cases. So let's find where that information is available in the output file. To find the base shear for your static seismic load cases, we're going to scroll down from the top of the output file, and we will find the calculation for each of the static seismic load cases. Here we're going to notice that the design base shear in the x direction is 239.46 kips. If I scroll down a little bit further, I can see that in the z direction it is also 239.46 kips. So we're going to make a note of that number. Next, we're going to check our base shear results for our dynamic seismic load cases. And again, I can use these quick links for the participation factors to jump to that area in the program. I'm going to be looking at the base shear for my first dynamic seismic load case in the X direction using the CQC, or complete quadratic combination method. Here for this first load case, I can see that my base shear is 211.26 kips. If I scroll down even further, I can get the base shear information in the Z direction as 215.03 kips. Now, what am I going to be doing with this information? So according to the ASCE 7, the value for each force-related design parameter of interest, including story drift, support forces, and individual member forces for each mode of response, shall be computed using the properties of each mode and the response vector defined in either section 11.4.5 or 21.2 divided by the quantity of R over I. So this code requirement has actually already been incorporated into the model through the scale factor parameters that we set within each of the modal response spectrum load items. Let's go ahead and take a look at another section of the code though. According to the ASCE 7, section 12.9.4, the combined response for the modal base shear is less than 85% of the calculated base shear using the equivalent lateral force procedure, the forces but not the drifts shall be multiplied by 0.85 times V over VT. Now, using the results of the output file for the IBC, equivalent lateral force procedure, and the IBC modal response spectrum procedure, we are going to check if the dynamic loads are within the code requirements or if an additional scale factor needs to be applied. So let's go ahead and take a look to see how those values are calculated for our particular model. Now, since the combined response for the modal base shear is greater than 85% of the calculated base shear, the dynamic analysis is already fulfilling the code requirements as outlined in ASCE 7, section 12.9.4, and no additional scale factor will be required for this particular model. Now, if the combined response of the modal base shear is less than 85% of the calculated base shear, you will need to adjust the scale factor, which is done right within the modal response spectrum load items for each of the dynamic load cases. Now, if after you perform your complete design, any of your dynamic masses, including the self-weight of the structure or the stiffness matrix changes, you may need to revisit the results of the dynamic analysis to ensure that you're still fulfilling the code requirements. Now that I have performed my dynamic analysis, generated my loads, and reviewed the results, I can see that I have achieved most of the code requirements as specified in section 12.9 of the ASCE 7. So at this point, I'm going to go ahead and proceed to the post-processing mode where I have some additional results available to me. To access the post-processing mode, you can go to the workflow panel, select post-processing, and your mode shape information will be available. So if we take a look at our screen, we're at the displacements area of the post-processor. We can see the results of each individual mode shape if wanted. So to select any of your dynamic seismic load cases, we can select them through the Load pull-down menu. And you can review the results of each of the mode shapes that were included within your calculation. You can also perform an animation of these mode shapes if wanted. So this concludes the process of generating your seismic loads, your dynamic seismic loads according to the modal response spectrum procedure as outlined in the ASCE 7 section 12.9.